beginning with topological quantum field theory. It's a subject which I just started learning, and since I've just started learning it, my understanding of it is naive and very simple-minded, which possibly makes me a good person to give an expository tutorial. So what the plan of the 3 talks is that I will give a purely expository tutorial, perhaps mentioning the word category once or twice at most. Definitely no profinite groups or anything like that. And it will be mostly physics-y. It will be about the physics, the physical phenomena that we believe can manifest anionic behavior. That's the so-called fractional quantum Hall effect. I'll also say something about what anions are, where they come from, and why we think they exist. And it will be a lead-in to Eric Paget's talk, which is about formalizing a lot of this stuff using the language of modular tensor categories. So there's been a lot of talk this week about the use of categories to formalize aspects of quantum mechanics and really probe what are the structures that one needs to do various things in quantum mechanics. So this will be slightly different. It's not so much foundational, but really pushing the idea that you need category theory to actually do computations, to calculate things in topological quantum field theory. That really is a natural calculational engine for the subject. So that will be a slightly different motivation than the foundational one. And finally, John Yard, who will give the last talk, will apply this to questions in like computing the Jones polynomial for now. Okay, so first of all, so as I said, it's going to be a very physicsy tutorial. Some of you are professional physicists who know a heck of a lot more about this than I do. So you can either close your eyes and ears, or you can interject when I say things that are too naive and need to be corrected. So let me begin with something called the spin statistic theorem. So when I was first learning quantum field theory, I was told that there are 2 theorems in the subject. One is this one, and the other one is a theorem called the PCT theorem. And what I mean by saying these are theorems of the subject is that these are theorems that hold for general relativistic quantum fields. They're not artifacts of this or that particular specific model. It's not a fact about the standard model or any other model. Any reasonable relativistic quantum field theory has to satisfy these 2 theorems. I need to tell you what these theorems are, and in order to do that, I need to first tell you what spin is, then what statistics is, and then what the theorem is. Sorry? Then what the theorem is. So, first of all, spin is really a fascinating thing in quantum mechanics, and of course you all understand it intuitively. Everybody who's done quantum computing talks about spin up and spin down as being the 2 states of a 2-dimensional quantum system. But why the spin up, spin down? So here is a fact. So particles in nature. So fact means that this is something that we observe, and it's not come out of some mathematical hypothesis. So a fact, particles in nature have either integer spin or half integer spin in some units, some natural units. Okay, so we don't see any other kinds of particles in nature. So why is this? Is there a group theoretic understanding of this fact? So it comes about by looking at the rotation group. And if we're talking about spin, here we're talking about some kind of intrinsic angular momentum. We are then concerned with how do these angular momentum vectors transform under rotations. So we transform under rotations by the rotation group. So the rotation group is affectionately called SO3. So it's a special orthogonal group. Okay, so it's a group of orthogonal transformations that keep the Euclidean distance fixed. Special means determinant plus 1. Is that right? Plus 1. Yeah. Now this group is not simply connected. Which means that it has loops on it that are non-trivial, that cannot be continuously deformed to the trivial loop. The trivial loop, of course, is just a point. So SO3 is not simply connected, and as such, if you look at it, you will find, as I said, loops that cannot be shrunk to 0. So I'm going to demonstrate this with my belt in a minute. So is there a better group that has a simpler topology? Yes, there is. It's called SU2. Sounds like a rap song, but it isn't. It's a group. And there is a map like this, which is continuous, which is both continuous and a homomorphism, and I think also an open map, right? And it's a double cover, so the inverse image of every point here is 2 points there. It sort of covers SO3 twice, but this is simply connected.
What is the SMS here?
Special.
Yeah. How does it distribute this?
Determinant plus 1.
Also, okay.
So you want to be in the connected component of the identity. If you don't want to have some discrete transformations thrown in there. So you're sticking in the connected component of the identity.
Is this to see on a block sphere or what?
And you're taking out the phases.
Take out the phases.
Yeah.
Okay.
So doesn't SO3 have 2 components? It has 2 connected components, right?
O3.
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 Yes. And S keeps you in one of them. Right. So if you look at the representations of SU2, you will find, you can ask how do they behave under the action of SO3. So it turns out there are things that change sign under a 2-pi rotation. And revert to the identity, revert to their original configuration. Under 4-pi. There are, of course, other things that revert to themselves when you give a 2-pi rotation. So, how will you be my assistant? Okay, so this is called the belt trick. I took it off in a glance so it's not well on me. So here's a belt. You see she's holding it at one end fixed. Okay, so that end will stay fixed. She's not going to twist it or move it, right? On this side is the belt buckle. So I'm going to give it a 360-degree rotation. So you would normally think when I rotate something by 360 degrees, that's the same as doing nothing. Okay, so you see there's a twist in this belt. The question is, can I continuously deform this twist away? Right? Because if it really is identity, this should be deformable to doing nothing. And you find, basically, no matter what you do, the twist is still there. Okay, so of course that's not a proof. I really demonstrated that one particular motion isn't deformation, but I think if you play long enough, you will very, very quickly convince yourself that you can't really eliminate this twist just by moving things around. Now I give it a second twist. Okay, so this is now got a 4-pi rotation. And now you see it's easily deformable to the identity. So there are things in nature, not exotic things, but things like my belt, which behave like spin half representation. Okay, so the representations.
Have you seen the glass version of that? Where you hold a cup?
I'm not young enough for that.
That's the 2-pi. That's the 4 pi.
Wow!
That's the Dali dancing move. Doesn't work with Prakash.
What?
Okay, so
That works perfectly.
Everything
So
works.
you just don't do whatever.
when I first took my course in particle physics, I expected that I'd be learning about lots of different kinds of particles with exotic names like omega minus and lambda hyperons and so on. Instead, what they said was, everything in nature is governed by groups. And so the entire course was a course on group representation. So, you see, classifying the representations of SU2 gives you a classification of the kinds of particles that there could be in nature. Similarly, classifying the representations of the Poincare group give you the kinds of wave equations that could be made in nature. So there's another thing that we could consider, and that is the interchange of particles. Okay, so now in quantum mechanics, particles are indistinguishable. Okay, so what this means is that you can't even mentally attach labels to them. And even if you say these are unobservable labels, you can't mentally attach labels to them when you're counting the statistics. They really are fully indistinguishable. So this means, in particular, the permutation group acts on the state space. Alright, so let's just consider two particles and consider their interchange. So I'm drawing dotted arrows because I don't mean that I'm sort of continuously deforming them. I just mean I'm interchanging the two of them. And you can ask, how do they behave? Well, if I interchange them once and interchange them again, then everything should be back to where it was. So definitely the square of this operation should be the identity. So what does, so let's say that operation is sigma. So we want sigma squared to be the identity. So what could sigma be? So sigma can only have two possibilities. It attaches a factor of plus or minus 1. Right? So now you see two curious things here. There are things that either change sign under a rotation of 2 pi or they don't. So the ones that change sign under 2 pi require 4 pi to be brought back to themselves. Here are things that are either flip their sign under interchange or don't. So the split statistics theorem, which I'm also going to prove, says particles carry half integer spin they change sign under interchange. No reason why this should have been true a priori, because I'm defining two completely different things. But they are connected in this intimate way, and of course, its behavior under interchange dramatically influences their behavior. So, for example, particles that don't change sign under interchange are called bosons, and particles that do change their sign are called fermions. What happens with fermions is that you can't put two of them in the same state. So if they're absolutely in the same state, and you interchange them, nothing changes, right? Because they're in the same state. On the other hand, the sign of the state is supposed to have changed. So what's the only thing that's equal to its own negative? 0. So obviously there is no state like that. You cannot put two particle state or two fermions in exactly the same state. And this has, as I said, a very dramatic effect all around us. It creates chemistry. Right? Otherwise, all the electrons are clustered in the ground state, but they don't. They form levels, and they're forced up by this, essentially by what is now called the Pauli exclusion principle. even more dramatically, they're responsible for white dwarf stars, which are supported by essentially by the exclusion principle. So those are fermions. Bosons are things that don't mind at all being intimate with each other. They just cluster in the ground state unless they're heated up and need to be moved out. So there are all kinds of dramatic phenomena, superconductivity, superfluidity, lasers, and so on, which are essentially manifestations of bosonic behavior. Yes?
So if you put two fermions at each other with very high energies, they will briefly get very close, right? Can they get arbitrarily close, or?
No, they ease off just before they get
But the
out.
point is you need more and more energy, I guess, to get them.
Yes.
both.
We definitely can put.
Yeah.
We definitely can.
Oh, I see.
Well, yes, they're quite happy if one is spin up and one is spin down, for example. And they're quite happy to form pairs in other ways. So superconductivity is actually two fermions that have been weakly coupled together and act like a boson.
A small footnote on there are examples of hypothetical particles that don't just go exactly necessarily to the same state when you exchange them. That's called parastatistics. Parastatistics.
Right,
And you end up with a what?
I said I always thought those were considered paranormal.
Well, in some sense they are. They don't exist. It's known, although Wally Greenberg claims you can think of quarks in that way. It's an equivalent way of thinking about color.
But you can consider such particles as examples of anyons, which is what.
No, this is not anion. It's nothing to do.
Parafermions.
No, this has nothing to do with anion. It has to do with something special in two dimensions. But this is just to do with the permutation group itself.
Yes, that's right. So
permutation
anions arise because they carry representation of the braid group instead of the permutation group. So this is just the permutation group. I was trying to suppress two weird things because I've been showing enough weird things. But anyway, I'd like to prove the spin statistics theorem. Yes, Nansa?
Something I don't understand. Where does the action of the permutation group comes from? Like it's a simple system, so I don't have names for my particles. But there's no, they don't have a number attached. They're not like point in the sets or nodes in the
But
graph.
they might have locations, right? So I might have a wave function for two particle
Alright.
systems like that.
Okay, so you need space to talk about. You want to exchange their positions.
For example.
Yeah. I mean, your point is good. If they don't have labels, why do they have labels there? And why is there x1 and x2? There's a way of doing that topologically where you actually, but that's a more fancy thing where you just work with the quotient space. And then you talk about bundles. Anyway, there's another way of doing it where you never introduce labels.
So
But
that's when you quotient space by the permutation group,
Yeah,
and
that's
you have this tiny non-simply connected space, yes.
yeah. But maybe the most physical way to think is that what Prakash, I mean, there's an actual physical process of exchanging the two particles. And if you do it adiabatically, then you can.
So why
Well,
don't you think around
there's
that?
subtleties, but I'm ignoring them.
Proving the spin statistics theorem.
He's preparing his proof.
There we go.
Do you want your assistant?
You can
No,
do-
no, I don't need my assistant. So I thought I'd prove the spin statistics theorem. Not the rigorous proof that you see in books like PCT spin statistics and all that. But this is something called the rubber band lemma, and it's due to Finkelstein and Rubinstein, or at least that's the first time I've seen it. Is it older than that?
It's the first time I've seen it also.
Okay, so in a paper in 1968, Finkelstein and Rubinstein proposed this thing called the rubber band lemma. And essentially what they said was, there's a deformation from this transformation to the rotation at one thing by 2 pi. And so you see, on one side, so I can't really call them particles because they're extended like objects. I hope all of you can see it. You see, I'm interchanging these two things. So this can be deformed to a rotation. Unfortunately, I've got the 2 pi distributed across the two strands, but it's supposed to be a 2 pi rotation in one of the strands. Okay, so you see that this can be deformed to that. And that gives you an explanation why this transformation behavior seems to be related to that transformation behavior. Okay, so several people, most notably Raphael, have actually pursued this kind of topological explanation for the spin statistics theorem. You want to say anything about it?
Well, in a sense, it said everything. But I suppose I could say that the work was never complete, in the sense that it would be nice to be able to claim that all manifestations of the spin statistics theorem, and there are many, have a topological root. And in fact, it's only really established for particles that are extended objects, like fermions and what are called kinks and things like that.
So in fact,
Whereas, in fact, if you look in a textbook for the spin statistics theorem, you're very likely to find something that involves notions like positivity of the energy and Lorentz invariance and analytic continuation of the...
I'm about to say...
Oh, you're going to say all those things?
Yes.
Okay. So there is a topological proof, and it's a kind of schema that you could in principle fit anything into, but not all the proofs have been fit into that schema yet.
Right, so recently I was reading a discussion that ensued. So somebody posed the following question in an issue in a letter to Physics Today, asking for an elementary proof of the spin statistics theorem. So what's meant by an elementary proof? So contrast this with the standard textbook proof of the spin statistics theorem. So the spin statistics theorem was originally used Pauli and a bunch of other guys around the same time had closely related ideas. So if you look up the article that Eric and I are writing, you will find many more citations. But anyway, Pauli is the name most associated with the spin statistics theorem. These arguments are finally refined. I think their most refined form appears in the book by Streeter and Whiteman called PCT Spin Statistics and all that, and depends on the following assumptions. Spin stat holds. If one, you have Poincare invariance. Only the French get this joke. Energy spectrum bounded below. So there's the lowest energy state called the vacuum. And then some more technical assumptions. Annihilation operators kill the vacuum. Locality assumption. Locality assumption is exactly what Rick talked about in his presentation of algebraic quantum field theory. Things that are space-like separated, commute or anti-commute, depending on which type of field they are.
So what does vacuum there mean? That's just saying the lowest energy?
Yes, there is a lowest energy state. I'm calling it the
And it
vacuum.
can be degenerate.
Yeah, definitely. So this means Poincare invariance.
I think probably in the Whiteman axiom, which
Why?
doesn't look exactly like this, I think the vacuum can't be degenerate. I think it has to be a unique state.
Oh, yeah, right. I think in the Weissman axiomatization it has to be a unique state, yes. But I believe spin statistics holds even with degenerate vacuum.
I don't know.
Anyway, so
Why
you
is
see
that Poincare invariance?
why Poincare invariance?
You want to explain for us yourself, no?
Point carré square.
Oh.
That's Poincare. Anyway. Right. So there was a lot of arguing back and forth between various people about whether you could do the proof and essentially souping up the elementary presentation I gave of the rubber band lemma. And there was a long review article written by Duck and Sudarshan saying that all these proofs based on topological things are bogus. Well, they didn't quite say that, but that's, I think, their intent. On the grounds that elementary particles are elementary, and these kinds of topological arguments apply to extended objects. Right? And this rubber band really depended on the thickness of the band. It was Jay was offering to lend me a hair elastic, and I said, no, I can't prove the spin statistics theorem with the hair elastic. I need a flattened band like that. So elementary particles, on the other hand, are supposed to be, at least electrons, are supposed to be structureless point particles. And how can this kind of topological argument apply in that case? Arthur Whiteman weighed into this debate too by saying, if you don't have Poincare invariance, you kind of have non-relativistic quantum theory. Then he gave counterexamples showing that you really did need Poincare invariance. It can't just be some kind of simple topological argument. And last night, John Yard told me that Pascal has a proof that depends only on the existence of antiparticles. But of course, one can say that's a consequence of Poincare invariance. But I haven't seen his proof. But if it's true, it's kind of extracting out the essential ingredient of Poincare invariance that's necessary for this proof to go through.
Question? Do you need an energy gap in your Hamiltonian so that you have stable particles? You can talk about, if you have massive particles, what would it mean? Does it still work?
Yeah. Don't see why it could happen. So as I said, it's a very general theorem.
It seems like there's like subtleties that can come with massive particles. Like photons are bosons, but they lose a degree of freedom, so they kind of act like.
They definitely still act like bosons.
It's still boson.
Yeah.
Okay. So now I better start talking about anions. So two things to note. All this discussion about things moving around, the rubber band lemma and so forth, applies in 3 dimensions.
Well, let me make just one comment. I mean, I think it's right that I'd like to see this proof, because I think it's right that it does ultimately depend more than anything else on the existence of antiparticles. But once you have antiparticles, you can make a topological proof.
Ah.
That's the things that Ball and I and some other, Beppe Marmot and so on, worked out in one version, one formal version. But there's a couple of assumptions that you make in this topological proof, which are just assumptions. And what I don't, when I said that you couldn't reduce everything to that, I meant I don't know how to justify those assumptions from the usual, say from the Whiteman axioms.
Right. So did you participate in this debate with
No, I didn't even know of this debate. I know George has a particular, he has his own proof that he likes.
What's the
Duck.
When was this debate taking place?
Between 97 and now.
Oh. Yeah, okay. So by that time I had stopped working on spin statistics.
Okay. So whether or not you accept these topological arguments, it does depend on 3 dimensions. So what if you're in 2 dimensions? And what if you have extended objects and not point particles? Okay? So essentially, the following observation was made by Wilczek. This form of the spin statistics theorem doesn't hold, and you can have particles confined to 2D. Can pick up any phase.
Now I have to make a historical comment though. I mean, Wilczek and I discovered this at about the same time, but he thought of it as more interesting than I did. But neither of us really were the person who really discovered it before that, which I'm sure, who doesn't always get the credit. It's Jan Meerheim and I think John Magnus is his first name, Linus. So the real people who discovered anions were Meerheim and Linus, L-E-I-N-A-A-S.
Gosh, never heard of them.
You see? So one is better at self-promotion than the others.
Yes, yes, having a Nobel Prize helps. All right then. Wilczek and others discovered that. So Wilczek did give this name anion. The idea
He can get credit for the name, right? But the concept is Mirheim.
anion. So the idea being exactly, it can be any old thing in terms of what phase it picks up. Okay, so these anions I want to talk about. These anions are the key to topological quantum field computing, and I'm not going to explain what TQFT is. What I'm going to do is I'm going to give a very short, very sketchy account of an experimental phenomenon where we think we have seen anions. Okay, and this is called the Hall effect. It's called the fractional quantum Hall effect. So I figured that you wouldn't understand the fractional quantum Hall effect unless you first understood the ordinary quantum Hall effect, sometimes called the integer quantum Hall effect. And I figured you wouldn't understand that if you had never heard of the Hall effect. So of course the physicists here have studied this stuff probably as undergraduates, but I'm going to start with the Hall effect. Okay, so I did promise very few equations, but here's one. Written in gloriously physicsy style. This is called the Lorentz Force Law. Okay, so it says the force on a charged particle or charged cube moving with velocity v and subjected to a magnetic field B has this force acting on it. Okay, so this is the famous three-vector cross product, which you've no doubt all learned about at some point or the other. Funky rules for which direction the cross product points in involving swimming and curling your hands. As you can remember, engineers taking courses and suddenly them all contorting themselves in the exam, trying to figure out which way the cross product goes. Now, what Hall did, so Hall was Edwin, is that his name? Edwin Hall? Or was that Edwin Land? Some kind of Hall. I don't remember the first name. Anyway, Mr. Hall. In 1879, which is a very notable year, the year Einstein was born, did the following experiment. He took a thin sheet, of course what he called thin, by today's standards, monstrously thick. Okay, so even though I'm saying thin sheet, it was actually a very three-dimensional experiment. And what he did was, he had an electric current passing through this. Okay. And of course, you have an electric current, you can measure the voltage. And there's this famous law discovered in the Vedas, it's called the law of Ohm. And it says the voltage equals current times resistance. So you can measure the voltage and the current and determine the electrical resistance through this thing. Now, if you apply a magnetic field perpendicular to this thin plate, of course these moving charges will get affected by this, and I believe they will be deflected this way. So the charges are normally flowing like this, the magnetic field is like that. If I've got the cross products right, they'll be deflected this way. So that means there will be a voltage that you will detect across the direction of the normal flow of the current. And you can measure the resistance associated with that. So the normal resistance R is measured this way. The resistance across this is called a Hall resistance. So this is the Hall effect.
Don't you have to measure current across to compute the resistance?
Yes. Measure voltage and current. So you get a Hall resistance associated longitudinally to the standard flow of the normal current. Now,
the current is longitudinal. So it's like there's a tensor associated with the resistance or the conductance.
Right.
This
Yeah,
is an
sorry, I didn't
orthogonal
mean that there's a current
component.
flowing like this. Right. Yes, so the resistance is no longer a scalar. It's developing voltages in directions orthogonal to the earth and so on. So this Hall resistance, you can measure its dependence on B. And you will find, so I get this right, increases with B. Yes, so increases with B. Which is not a surprise because there will be a higher Hall voltage as you increase the magnetic field, so they will be pushed even more and more. Similarly, it increases with decreasing current density. This means there are fewer electrons, so they have to be moving faster to generate the same current. So they're subject to greater force. So there's a standard dependence on B, and we get this nice graph of the Hall resistance versus the magnetic field, and it looks like that. Okay, so that's the Hall effect. Now, we take this, and instead of using this thin metallic plate, we take this 2D, two-dimensional system. Okay, that's typically obtained by trapping a fine layer of electrons between two layers of semiconductors. So actually, Patrick has written papers on stuff like this. Have you?
I have been an author on things.
Anyway, I'm not going to talk to you about gallium arsenide and impurities and oxidizing semiconductors, but the point is you can get extremely thin 2D electron gas. I say gas because it's really floating around, but it really is two-dimensional. It's not like Hall's thing, because even though this is thin by the standards of 1879, it's 10 to the 20 electrons across, I'm sure. Okay, but these extremely thin 2D electron gaps, so these surface phenomena were investigated at Bellairs and other places in the 70s and 80s. And Klaus von, never figure out how to pronounce the name, Huxley, discovered the following strange graph. So I'll show you the graph first because I said this would be experimental.
Okay. You're done with the classical Hall effect.
Yes.
So why something must be surprising, like else people would not call it an effect, right? So there must be something strange.
It was surprising in 1879. We teach it to freshmen now.
There is actually something else. What? I didn't hear that. But there's something surprising when you go to semiconductors that I don't suppose the original Hall effect discovered. But if you work out the sign of the voltage, it depends on the charge, on the sign of the charge carriers, right? So if they're electrons, it'll be one way. If they're positrons, if they were positrons, it would be the other way. And in what are they called? N-type semiconductors in which holes carry the charge, P-type, I guess. Semiconductors, the Hall voltage is just as it would be for positrons. So it's a very graphic illustration that the holes are real thing in a sense, things with a reality just like the electrons have, which is very hard to understand, right? Because if you think what's really happening microscopically when holes are flowing this way is electrons are flowing this way. And then you look at that argument Prakash gave, well, it's got to be the other. I mean, the electron, it's still really electrons moving, and the magnetic field is blah, 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 and the force is blah, blah, blah. So how can it be that the sign of the voltage changes? So that's a kind of paradigm. I mean, that's a kind of very
That's much
striking.
Hall.
But I don't think that has anything to do with the original. But it's not also to do with the quantum Hall effect.
No.
It's still...
So I only describe this because it isn't surprising. I wanted to prepare you for the surprise, which is right here. So
I think it's so. If you do this as a student, it's very surprising. But on the side of two things, You get a current.
But that's
Well,
what
you got no input and no output.
people knew magnetic fields would exert a force on particles at the time, so it's like the quantitative picture is not surprising, so I think it's not like
It didn't take me much to explain it. And I explained it in purely undergraduate terms. But anyway, for contrast, so Klaus von Schiltzing, I hope I'm pronouncing his name correctly, look at extremely low temperature, extremely thin 2D electron gas with very high magnetic fields and measured the Hall resistance. And what he found was anything but a straight line. So he found a number of, if you look at the Hall resistance, it's kind of wiggly over here, and it flattens out for a bit, flattens out for a bit there, flattens out for an even broader amount, and very broad plateaus. Okay, so what the heck is the reason for this? The reason, so the second thing, observation, which I won't attempt to explain, is that at these plateaus it becomes superconducting. Okay, but that's not so important. The important thing is why the heck do we have these plateaus? And they seem to come in jumps. So all resistance has these plateaus associated with that. Okay, where I is energy.
Is this at room temperature or
No.
what temperature?
I think 1.5 K.
So Prakash, you labeled them coming down like this. Is one the last plateau, but what happens after that?
That is the next topic, but I won't tell you just yet. Right, very good question. Yes, but let me not tell you that. So indeed, you might think that's the end of the effect. We should now go on and become like the classical Hall effect. So this was what Schiltzing observed, and it was subsequently explained by Robert Laughlin. So I don't really want to go into the details right now, but I'll point out some essential features. One essential feature is that it happens in 2D. The second thing is there are energy gaps. Let me try and give a hand-waving explanation without drawing anything on the board. All right, so just as you have an electron confined to an electric field of, let's say, a nucleus, you get a discrete spectrum of energy levels. Here also, in a very strong magnetic field, it's almost as if it's trying to push the thing into the electrons into circular orbits. This will be hand waving. And it ends up, well, not exactly with discrete energy levels, but with banded energy levels, with distinct gaps between the bands. So these things are called Landau levels. And what happens is that you slowly, let's say, as you reduce the magnetic field, the Landau levels go down, the gaps become smaller, but they're still there. And at some point, the Landau level is exactly filled. Okay, so now if you want to take electrons out to the next level, they have to have an energy jump. Okay? But it turns out there are lots of impurities, and these produce little local wells. And no matter how pure and ultra clean you try to make it, there will be these little impurities and distortions, defects in the two-dimensional lattice. And there will be little potential wells in which there will be sort of local Landau levels in which electrons are trapped. And they sort of leak out from here with no extra energy required to jump the gap, and that's what causes these plateaus, also what causes the superconductivity. It's a very universal phenomenon. It doesn't actually depend on this or that material or this or that impurity, and it is now the standard for measuring the electric charge. Okay. And the reason reason why it can be used as a standard is because there's this broad plateau. Since it is dependent on the precise value of the magnetic field, then of course it can hardly be used as a standard. But the fact that it's so flat there means you don't have to be as accurate in producing the magnetic field to get a very precise reading of the electric charge. The point is, this is completely explained in terms of the quantum behavior of electrons. But now, John asked an extremely interesting question, which is what happens after 1? I mean, there's nothing smaller, no integer smaller than 1, right? But of course, if you just asked this in time, you would have a Nobel Prize by now. if you redraw the graph. So some wiggling over here, let's say that's 2, that's 1. Oh, blimey, there was another. So that corresponds to 1. Corresponds to 2. We discovered something corresponding to 1/3. Okay, another completely inexplicable thing. As I said, you can use this to measure electric charge very accurately. So you can ask, what's the electric charge I measure corresponding to that plateau? Get an electric charge of E/3. Nothing like this has been seen in nature. One of the most sacred rules of quantum field theory is that electric charge comes in units of the electronic charge, never any fraction of it. Here's something that absolutely looks like it's got 1/3 of an electric charge. So yes, you've probably heard about quarks and so on, carrying 1/3 of electric charge, but we've never seen free quarks. These seem to be free particles with 1/3 the electric charge. Okay, so the point is, so Raphael made this remark about holes behaving just like particles. So here's this one. There are emergent phenomena. Emergent phenomena. So there are things that are best called quasi-particles, which behave just like particles, which means they have frequency, they have energy, they have momentum, they can bounce into each other and scatter, they can bash into electrons and transfer energy to them. And we have seen many quasi-particles before. So for example, we have things called phonons, which are quantized vibrations of a crystal lattice. Okay? And obviously, it's not a fundamental thing. It's like an artificial thing. You're kind of pretending that the crystal lattice is a field and its excitations are these particle-like things called phonons. But these phonons, though unreal, behave like they're very real. They scatter, they can be measured, they can be seen to bash into electrons and transfer momentum to them. And they can bash into each other and they behave exactly according to the laws. There are in superfluids things called rotons, which are little rings of fluid that just rotate freely in superfluids. And of course, those are also not real particles. They just seem to be like little bundles of angular momentum that are just floating around and which are emerging as the emergent phenomena. And they're not there in any fundamental sense. They're only there when you have a collective thing. And of course, holes in semiconductors, of course, are the prototypical example of this. So the proposal here, so Laughlin explained this as well. So the explanation of the fractional quantum Hall effect is in terms of emergent particles. Okay? So you've got this soup of electrons in a strong magnetic field, and excitations of this soup behave as if they were particles with 1/3 the electric charge. And because they appear to be there, you get this plateau, just like in the ordinary quantum Hall effect. But this cannot be explained by just talking about electrons. You have to talk about the effective field theory of these collected excitations. So what kind of things are these emergent particles? I won't go through a long story because I'm running out of time. But roughly speaking, these particles essentially they look like this. This is the last piece of my multimedia show. you have some kind of extended object, which is the excitation, but attached to it is a cube of magnetic flux, a so-called flux cube. So these things look like packets of charge. Okay. It's only collectively that it behaves like 1/3 the electric charge. There's certainly no single entity there with that charge. So we've got packets of charge with attached flux tubes. So it's like quantized magnetic flux tubes. So the right way to describe these things is as extended objects with ribbons. And that's what they are. Right, so now you see the motivation for studying ribbon categories and so forth. It's because there are ribbons out there. So we have to study them, we have no choice. Okay, so let me say a bit about fusion rules. Now of course, since these are emergent particles, when you combine them, not at all obvious what will happen. It's very clear what will happen when you take one electron and another electron, and you put them together, by golly, you get 2 electrons. But when you take one of these things with another one of these things and put them together, some complex interaction happens and some new kind of gizmo appears. Okay? So, combining these things will give new types of things. New types of things. So we need to keep track of type description of these kinds of gadgets. This is what makes the categorical description, I think, absolutely essential here. It's not just there as a fancy superstructure. It is, I mean, this is what category theory is about, in my opinion. It's a type, introducing types into nature. And it's absolutely essential to do that here.
Because they are finite, many types that is created.
Sorry?
This number of different types that comes out, they are finite.
No,
So obviously you can
may not be. But of course, we're unlikely to see more than a few types because, you know, it involves higher and higher energies and harder to create experiments.
Is it possible that some of these old things get together and create one of the things that was one of them?
Yeah, absolutely. So, rules for how these things combine are called fusion rules. So fusion rules basically tell you, I've taken this type of anion, I've taken that type of anion, I put them together, and I see, what do I see? All kinds of possible different things. So how is this described? The formalism looks like this. So let's say phi sub A means anion of type A. And let's say I use this thick dot to mean I fuse it with an anion of type B. I may get a sum, so these NABC are integers. NABC are integers, and they basically tell you what kind of other anions are produced. Okay, so typical example of fusion. So these are called. I'll give you an example of fusion rules. Called Ising anions, and the fusion, so they come in 3 species of them, of these Ising anions, and when you combine them, they obey this kind of fusion rule.
number is the charge?
No, this is just a label.
This,
The name 0, half, and 1, they could be called alpha, beta, and gamma. That number half means nothing.
But you have the trivial charge, which is 1 for the left operation.
Actually, it's 0.
0, sorry.
But I mean,
So,
there's no significance to the half.
what's the significance of having times on the left but plus on the right? So the times means when two such things meet, but what does the plus mean? Does it turn into a 0 and a 1, or
Yes.
into a superposition of 0 and 1?
Sorry,
it's a
or.
disjunction.
It's a measure.
Or means superposition?
It's collapsing the state.
It's,
Oh, okay, right.
it's as in Pletism.
So,
Right.
so it really becomes one or the other.
Yes, yes, it becomes one or the other. Right.
But there's no probability? Oh, I see.
There will indeed be probabilities.
Because they're
but
the ends of ABs.
we won't talk about that. So this may remind you of the kinds of rules that you would have seen, for example, when you were adding angular momentum. Right? So there are rules that say if I take a spin half particle and a spin one particle and I add them up, well, of course you can go back and do Pletism and say I'll take the tensor of these two irreducible representations and decompose that into new irreducible representations, and you discover that you've got a spin half and a spin three halves, for example. So this formally resembles that. There's also something called the 6J symbols. So the 6J symbols are now telling you things that may not be familiar to most of you, just to connect up some terminology that Eric will introduce with things that you might know. So the 6J symbols basically allow you to change the basis of the vector space that you get when you combine representations of SU2.
Where the vector space can be different.
So that's where representations live, right?
Is this combined Christoffel symbol?
Not Christoffel, Wigner 6J symbol? I don't really know. I don't think Christoffel symbols are something to do
Not Christoffel, no.
with curvature and so on.
Maybe you're thinking of Klepsch-Gordon.
Klepsch-Gordon, that's it. Yeah,
Klepsch-Gordon,
They're
yes,
like
closely
That's the
related.
one, that's the one.
Starts with
That's
C.
the one.
Closely related to Klepsch-Gordon. I just want to say one thing, Peter, which is that the analog of those Klepsch-Gordon symbols are, in this context, called the F matrix, which basically changes the basis from in these composite state spaces of the anyons. Okay, so I've given you the ingredients for Eric to lead in and make it all categorical. Yes?
Oh, I had another question about the cubing rules. So are they all left to right, or can they be right to left? So does the number of particles always decrease? Or can a 0 turn back into 1/2 times 1/2?
I believe it's left to right.
So after a while they should all disappear, right? Because, well, when 2 meet, they turn into 1. So the number always decreases of these emergent particles.
It can go in reverse. You can have a splitting as
Oh,
well.
if you can go right to left as well.
You can have splitting.
You can have splitting.
Just that.
That's fine.
Related question, is this unitary?
Yes.
Then it should be a coherent superposition of 0.
But then 0, 1 are not the quantum states.
It
So
measures.
that's the thing. It's unitary not over the anion
I
space.
think I will clarify it.
Oh, Okay, in that case, I will stop. But before Eric starts, I just want an administrative break. May want to turn that off unless
Sure.